Welcome back. Today we will continue our exercise 2.1, the third lecture on that exercise, and the topic is examples on applications of derivative to geometry, velocity, rate measurer. The first example, the volume of surface sphere increase at the rate of 20 centimeter cube per second. Find the rate of change of its surface area when its radius is 5 centimeter. So what is given? It is the problem is related to the volume, surface area, and the radius of the sphere. So let V be the volume of the sphere, A is the surface area, R is the radius of the sphere respectively. Then what is the volume? Rate of change of volume is given. It is dV by dt, 20 centimeter cube per second. Also radius is 5 centimeter. And we want to find the rate of change of the surface area. Now what is the formula to find the volume of the sphere? It is V is equal to 4 by 3 pi r cube. So differentiate with respect to r. We get 4 pi r square. But it is given that the rate of change of the volume is 20. So put the value here and simplify it. We get 4 pi is equal to 20 upon r square. Now the surface area of the sphere is A is equal to 4 pi r square. Again differentiate with respect to r. We get 4 pi 2 times r. It is 8 pi r. But what is here r? Or what is the value of 4 pi? It is 20 upon r square. So dA by dr is 40 upon r. But r is the radius is given. It is 5 centimeters. So put r is equal to 5 in dA by dr. You get 8. So the rate at which the surface area is changing when the radius is 5 centimeter is 8 centimeter square per second. The next example, a man of height 2 meters, walk at a uniform speed of 6 km per hour away from the lamppost of 6 meter high. The height of that lamppost is 6 meters and the height of the man is 2 meters. And the man is going away from that lamppost and the speed of the man is 6 km per hour. We have to find the rate at which the length of the shadow is increasing. Here, this OA is the lamppost. This MN is the man whose height is 2 meters. The height of this lamppost is 6 meter. This X is the length of the shadow, and this Y is the distance between the man and the lamppost. The man is going away from the lamppost at the rate of 6 km per hour. That means you have given dy by dt. dy by dt, that is 6 km per hour, and it is x is the length of the shadow. So dx by dt is the rate at which the length of the shadow is changing. So the rate at which the shadow is lengthening is dx by dt. Now here B is the tip of the shadow and its distance is x plus y from the lamppost. So this is the distance x, this is the distance y. So this B, the point B, tip of the shadow is at a distance of x plus y from this lamppost. So using the result from the geometry, this x upon 2 is equal to x plus y upon 6. So cross multiply and simplify, you get 4x is equal to 2y. So x is equal to y upon 2. Differentiate with respect to t, we get dx by dt is equal to 1 upon 2 dy by dt. So what is dx by dt? It is 1 upon 2 times 6, as dy by dt is given 6. So what is dx by dt then? 3 km per hour. The length of the shadow is increasing at the rate of 3 km per hour. Now a man of height 1.5 meter. Now here the height of the man is 1.5 meter. He walks towards a lamppost. Now he walks towards the lamppost and not the away from the lamppost. And the lamppost is having height 4.5 meters at the rate of 3 by 5 meter per second. Now we have to find the rate which shadow is shortening. Now as the man is approaching to the lamppost, his shadow will be shortening. If he goes away from the lamppost, his shadow will be lengthening and the tip of the shadow is moving. Similar figure we will draw again. Here is his OA is a lamppost, this MN is the man, this MB is X and this OM is Y. So and the rate at which the man approaching the lamppost is given that 3 by 4. That means dy by dt is given 3 by 4. And the rate at which the shadow is lengthening, that means decreasing. The shadow is shortening is dx by dt. And the B is the tip of the shadow and is at a distance of x plus y from the lamppost. So again you will use the same result, x upon 1.2. This x upon height of the man was 1.2 is equal to x plus y upon height of the lamppost, that is 4.5. So cross multiplying we get x is equal to 0.5 y. So differentiate with respect to t, we get dx by dt is 0.5 times dy by dt, and this dy by dt is already given 3 by 4. So 0.5 into 3 by 4 is 3 by 8 meter per second. So the rate at which the shadow is shortening is 3 by 8 meter per second. Shadow is shortening 3 by 8 meter per second, and the rate at which the top of the shadow is moving, tip of the shadow is moving, is given by d by dx of x plus y. So d by dx of x plus y means dx by dt and dy by dt. So we will put those values of dx by dt and dy by dt in this equation and we will take the addition of 3 by 8 plus 3 by 4. It is 9 by 8 meter per second. So tip of the shadow is moving 9 by 8 meter per second. The next example is a ladder of 10-meter long is leaning against a vertical wall. If the bottom of the ladder is pulled horizontally away from the wall at the rate of 1.2 meters per second, find how fast the top of the ladder is sliding down the wall when the bottom is 6 meters away from the wall. This is the ladder. This is the ladder whose length is 10 meter. And we are taking away this bottom of this ladder away from the wall. So this the top of the ladder will gradually come down to the bottom of the wall. So this AC is the wall and AB is the ladder whose length is 10 meter. So the dx by dt is dx by dt means rate of change of going away from the wall is 1.2 meter. Now we want to find dy by dt. So the by using Pythagoras theorem, we can write that x square plus y square is equal to 10 square. So that is the 2x dx by dt plus 2y by dy by dt is equal to 0. So dy by dt is minus x by y dx by dt. When x is equal to 6, equation 1 becomes a 6 square plus y square is equal to 100. So y is equal to 8. So equation 2, we will put the value in equation 2. dy by dt is equal to minus 6 by 8 into 1.2, that is minus 9 by 10, that is 0.9 meter per second. So top of the ladder, this top of the ladder will go down at the rate of 0.9 meter per second. So for 1 second it will move to 0.9 meter, that means approximately 1 meter. We can say that approximately 1 meter that is moving down. The 16th example, if water is poured into a inverted hollow cone. Now what is mean by inverted hollow cone? This is the cone and this is empty inside. This is empty. This is axis of this cone, and this angle is 30 degree. Okay, this is semi inverted hollow cone, and we are pouring the water in it, and the rate is the depth increasing at the rate of 1 centimeter per second. So this is the information given. What we have to do, find the rate at which the volume of the water is increasing when the depth is 2 centimeter. So dH by dt, rate of change of the height, is given 1 centimeter per second. We want to find the rate of change of the volume when h height is 2 centimeter. Also it is given that the theta is 30 degree, that means the semi-vertical angle of the cone. So tan 30 is opposite, tan 30 is opposite upon adjacent, so r upon h. So from this you get 1 upon root 3 is equal to r upon h. So h is equal to root 3r, or r is equal to h upon root 3. So we must know the volume of the cone. What is the volume of the cone? What is the formula to find the volume? It is V is equal to pi by 3 r square h. Now what is r then? R is h upon root 3. Put that value, r is h upon root 3. So you get h square upon 3. Now this 3 3s are 9, and h square into h is h cube. So pi by 9 h cube. Now we will differentiate this volume with respect to t. So dv by dt is pi by 9 3h square into dh by dt. 3 3s are 9. So pi by 3 into h square into dh by dt. So what is the h? We want the rate at which after the depth is 2 centimeter. So h is 2 and dh by dt is given 1. So pi by 3 into 2 square into 1, it is dv by dt is 4 pi by 3 centimeter cube per second. That means the rate at which the volume of the water is increasing when the depth is 2 centimeter is nothing but 4 pi by 3 centimeter cube per second. So this is the exercise 2.1. In next lecture we will start our approximation.